Welcome back. All the technical details for problem solving were discussed in the previous video. In this optional video, we're going to talk about the derivation of proofs. First, let's recap what we did. We talked about the nth term test for divergence, harmonic series, which is a bit of a minor deal for our purpose here. Geometric series is important. And then we talked about some nice little thing called Cauchy sequence theorem. It kind of goes like this. A sequence converges if and only if the difference of the general terms go to 0, where the difference of the general terms am and an are unrelated, except that m and n both go to infinity. For example, if m is n plus 2 or n is m squared, things like those, then they are not general enough. You really need to get unrelated m and n so that they are really arbitrary. Now, if we put those Cauchy condition to the partial sums of a series, then we have this one, Sn minus Sm. We're going to use the latter one to the proofs of, well, a lot of things as a matter of fact here. Oh, not this one. Let's go to this one. Okay, we have to talk about alternating series and the remainder, absolute convergence, ratio test, and a root test. Okay, let's go. Alternating series. Okay, that's the trickiest, but let's begin with this one. I don't want to change the order of the textbook too much. Let's begin with Cauchy criterion here. We want to estimate the difference between partial sums, Sn minus Sm, in absolute value. If we put those into this alternating series formula here, we have just subtraction, and then we have that from n plus 1 to n. And please make this observation. Depending upon where we start, this will be plus minus plus minus plus minus as we see here, or minus plus minus plus minus plus as we see down here. But then again, they will make no difference whatsoever because we are going to take absolute value anyway. So multiply -1 to everything down here, because we can do that within absolute value, and we're going to produce plus minus anyway, and that's this term down here, plus minus plus minus plus minus, and then you don't have to pay too much attention to the very end. It's going to be either plus or minus depending upon what's the last term. So the key is this one. This one is not really that important. Next one, bm plus 1 minus bm plus 2, bm plus 3 minus bm plus 4, and so on and so forth, pair up like this. So we have in the end last 1 or 2 terms there. And each parenthesis there is positive. That's a tricky step, and that's the ingenious thing as a matter of fact. Because what's the alternating series? Well, we have to have this condition. Absolute values steadily go down to 0, so bm plus 1 is greater than bm plus 2, bm plus 3 is greater than or equal to bm plus 4, and so on. So all these are positive. So we can throw away all the absolute values, and then we end up with this one, and that is greater than or equal to 0. Now let's manipulate this a little bit further. Leave the first one, and then take the next pair, and then the next pair, and the next pair, and then the last 1 or 2, last 0 or 1 terms, excuse me. And each parenthesis here will be negative this time because, well, bm plus 2 is greater than or equal to bm plus 3, and so on. So this is negative, and that's positive, so we have overall negative. Again, we have overall negative. We have steady decreasing down to 0. That's a remainder. That's a reminder, excuse me. So negative negative, and we are adding bunch of negative terms. So if I throw away all these negative terms, then you're going to end up increasing the value, and that's how we get this inequality. By the way, let's remind ourselves, where did we start and that ended up with all the equalities and inequality in the end? We started from here. So absolute value of Sn minus Sm is less than or equal to b m plus 1. And this one is just fixed value m plus 1. And if you take m huge, then let's go down to 0. That's going to go down to 0. And n is even bigger, so by taking the limit, well, the right-hand side, even bigger number, bn plus 1, is going down to 0. Consequently, we have the Cauchy condition, Cauchy criterion. Therefore, the series must converge. Well, it was very difficult to write, especially with all those indices here, but when even and odd kind of things. But if you skip those and then just use this last 1 or 2 terms or last 0 1 term, kind of like that, it's not that difficult to follow. Next one, how about the error estimate or remainder estimate? Well, let me remind you, we got up to here in the proof of the previous theorem. Absolute value of Sn minus Sm is less than or equal to b m plus 1 with a lot of difficulty whenever n is greater than m. Now, at this point, take the limit. Yes, you can take the limit because we just proved that the limit exists. So, take the limit, and Sn is going to s, and then the right-hand side is just upper bound, so it stays there. So by the limit rule, this one is constant, upper bound stays there. So what do we had? Absolute value of s minus sm is less than or equal to b of m plus 1. And that's precisely what the statement is all about, except that I changed m to n. So there you go, the remainder estimation. The upper bound of the remainder is the absolute value of the very next term. Now, let's move on to absolute convergence. If a series converges absolutely like this, then the original series converges. Well, okay, we're going to use Cauchy criterion again, and let's see. We want to prove that this one converges, so let's use Cauchy criterion for this one. Let's take the absolute value of the partial sums, then that's absolute value of Sn minus Sm, so summation from m plus 1 to n. And then let's pass this absolute value inside the summation. Here, when I highlight it here, some AK can be positive, some can be negative, so there can be some cancellation. If we take absolute values and then sum them up, then there's no cancellation, just adding all the positive numbers. So right-hand side is bigger than the left-hand side. But even bigger right-hand side, bigger number, this one is going down to 0 because this one is actually a difference of partial sum of this summation, this infinite sum given by absolute values. And we know that this one goes down to 0 by the Cauchy sequence theorem because we assume that the series of absolute values is convergent. So what do you get? Even the bigger quantity is going to 0, so this absolute value is going down to 0 as well, and we have the Cauchy criterion for this series. So we have the convergence. Conclusion, absolutely convergence implies convergence. Not vice versa though. Here's an example. Rearrangement, that's a bit too complicated, so I'm going to leave that to students. If you're interested, you can read some advanced book like this. Okay, how much time do we have? Let's talk about ratio test now. What if an plus 1 over an in absolute value is approaching to L, which is less than 1? Then we can say this quantity is very, very close to L, and L is relatively far away from 1 because that's strictly less than 1. Actually, what we can do is we can insert a certain number r between L and R, and when n is sufficiently large, this quantity is sufficiently close to L so that this one is less than R. I cannot say this one is less than L because some of them may be bigger than L, some of them may be less than L, but they're all very close to L, consequently less than R, because L to R is actually a non-trivial interval. So what do we get? Flip this denominator over to the other side, we get this. And do the same thing with an plus 2 over an plus 1, then we have something like this. And then do it again, then we have r squared an. Do it twice more, then an plus 3 in absolute value is less than r cubed times an. And just continue all that toward infinity, as a matter of fact. And this is what we're going to get. The tail part of the series, case going from n to infinity, is overestimated by, well, the starting quantity times r to the k power. But this one is geometric series, so it's bounded. So what we get? This sum of absolute values, is bounded. And then how about the tail part? That's finite all the time. K is running from 1 to n. That's just finite sums, so that's bounded too. So consequently, entire series is bounded. Entire series of absolute values is bounded. Consequently, we have to have convergence. Series of absolute values converges, so we have to have convergence too. So this is absolute convergence. Now what if L is greater than 1? In that case, an plus 1 is greater than an, so the general term does not go down to 0. So the nth term test for divergence applies. So we have to have divergence. Equals to 1, then this method fails. You have to find some other method. Let's see, do we have enough time for a root test? Looks like I can barely make it. Well, here we go. Let's do the same thing. We'll insert a certain r between L and 1 so that if this root is sufficiently close to L, then it should be less than r. You cannot say this quantity is less than L because some of them may be bigger than L, but they're going to be very close to L so that it's less than r. R is, well, non-trivially greater than L. So if you take the nth root, what do you get? Absolute value of an is less than r to the nth power. So if we sum them up from, well, n to infinity there, then we have a geometric series again. And geometric series is bounded. So what do we have? This highlight series is less than infinity. So tail part is bounded. Head part from, well, the finite sum, the head part is always bounded, so we must have bounded sum. The sum of the absolute values is bounded, so what do we have? We have an absolute convergence. Now, what if this quantity, this limit is greater than 1? Then what? Well, L is greater than 1, so an is greater than 1. For L is strictly greater than 1, then an is greater than 1 for infinitely many n values, as a matter of fact. So an does not go down to 0. So the nth term test for divergence applies again. So we have divergence. Well, there goes the proof for root test, ratio test, and then all these. I hope at least some of you followed most of it, but even if you didn't follow any of it, it's still okay. Any kind of exposure will help.